Good afternoon, my name is V. Pradeep Reddy and I am from Aeronautical A section. My heat and mass transfer topic is mass diffusion. Brownian diffusion. Small particles suspended in a fluid undergo random transitional movements due to molecular collisions. This phenomenon is referred to as Brownian motion. The Brownian motion leads to diffusion of particles in accordance with Fick's law. J equals to minus d into dc by dx, where c is the concentration, j is the flux, and d is the diffusion coefficient. When the effect of particle inertia is negligible, using the J equals to minus d dc by dx, the equation of conservation of mass for the particle leads to dou c by dou t plus v into delta c equals to d delta square c, where v is the fluid velocity vector. The mass, the particle mass diffusivity is given by d equal to kt cc by 3 by mu d, where cc is the Cunningham correction given by, and k is the Boltzmann constant. K equals to 1.38 into 10 power minus 16 erg per Kelvin. The diffusive may be rested as d equals to tau kt by m, where m is the mass of spherical particle and tau is the relaxation time. Brownian motion of rotation. The mean square displacement for a Brownian particle is given as a square equals to 2 dt. Aerosol particles may also rotate randomly due to Brownian effects. The mean square angle of rotation is given by pi square equals to 2 kt by pi mu d3t. Distributions. When the gas is in equilibrium, the aerosol particle will have the same average transitional energy as molecules. Thus, 1 by 2 mu square equals to 3 by 2 kt. And the root mean square particle velocity is given by under root u square equals to under root 3 kt by m. Particle diffusion to a wall. For a one-dimensional case, the diffusion equation given by in the absence of a fluid flow becomes dou c by dou t equals to t into dou square c by dou y square. For an initially uniform concentration of aerosols in the neighborhood of an observing wall, the initial and boundary conditions are c of y comma 0 equals to c naught and c of 0 comma t equals to 0. The solution of equation then becomes c of y comma t equals to c naught erf of y by under root 4 dt, where erf equals to 2 by under root pi limit 0 to e in power minus e square dou e. Variation of concentration profile with time. Temperature dependence on the diffusion of coefficient. Solids. The diffusion coefficient in solids at different temperatures is generally found to be well predicted by the Arrhenius equation. D equals to d naught e exponential of minus ea by rt. Liquids. An approximate dependence of the diffusion coefficient on temperature in liquids can often be found by using Stokes-Einstein equation, which predicts that dt1 by dt2 equals to t1 by t2 into mu t2 by mu t1. Gases. The dependence of the diffusion coefficient on temperature for gases can be expressed using Chapman-Enskog theory. D equals to a t power 3 by 2 by rho dou square 12 sigma under root 1 by m1 plus 1 by m2, where d is the diffusion coefficient, a is an empirical coefficient equal to 1.859 into 10 power minus 3 atm a square into c centimeter square by k power 3 by 2 under root g by molecule. 1 and 2 are indexed the 2 coins of molecules present in the gaseous mixture. T is the absolute temperature, m is the mass polar, P is the pressure.